Okay, thank you. I'm glad to see I actually have an audience today, so thank you for coming. Okay. Now, it was my 75th birthday last week, and I'm getting so old and bent, I can hardly lift my head to see the slides. So if I, look a bit strained. Okay, now my collaborators on this talk, essentially, which you see at the top, are Rahul Pandit and his students, Kiran and Navier-Stokes from Indian Institute of Science. And there's a bit of a story here. I was an organizer on the turbulence meeting in 22, and Rahul appeared in my office and sort of shunted the Toner 2 equations of flocking in front of me and said, how about looking at these? Which I had never really looked at flocking, swarming problems before. And so he introduced me to the subject. And if the boys are online, then good morning to you. Now, I'm going to concentrate on these two versions of what's called the Toner 2 equations. If you recall Sriram Ramaswamy's talk, where he gave the physics behind how such equations actually appear, and then what's called the Toner 2 Swift-Hohenberg equation. I'm going to consider these two very briefly. Now, when Rahul introduced me to the subject, I read many of the reviews. And they rightly say, of course, that turbulence in flocking and swarming is rather different than high Reynolds number fluid turbulence. And that's, of course, true from the observer's point of view. But from a mathematician's point of view, I actually want to spend this time showing you that actually there are many, many common properties. So I'm going to give like a tutorial talk from a sort of mathematician's point of view to show you the sorts of methods that my community actually uses and how it applies to both these equations. And to do this, excuse me, I'm going to just give you a couple of slides on, take you through the multifractal model. Most of you will have done this in graduate school. A very brief summary of some modern results on Navier-Stokes analysis and their correspondence with the multifractal model. And then I'm going to show you the whole point of the talk, that these properties, and I hope I will get through to you, will actually apply very nicely to the Toner 2 equations, and that therefore they actually possess the same properties. And then, if I have time, I will look at Toner 2 Swift-Hohenberg, which is of course different in the sense that it has anti-diffusion, my one chance of getting anti-diffusion into this program, with a bilaplacian. And this is very new ongoing work with Rahul and Kiran and Daniel Boutros, who's a student here in Cambridge. So let's start. Okay, well, just 3 slides. Classic slide on turbulence attributed to Richard Feynman. I don't know whether that's really true, who said that turbulence is the last great unsolved problem of classical physics. That's a very well-known saying. Less well-known is that by Hans Liebmann of Caltech, who said turbulence is a graveyard into which physicists think they can move and solve the problem, which I think is rather interesting. Now, I've stolen these 2 pictures that Uriel Frisch put on the web publicly, and it's the classic Richardson cascade process where you start with some sort of vortices and they split into daughter vortices and they split and split and split and you get a cascade of energy cascade and down to dissipation. Certainly that was Richardson's view. Those of you who've not read Peter Lynch's scientific biography of Richardson, it's a CUP book, it's very well worth reading, it's very good. Mandelbrot in the 70s, when he hit everybody with the fractal phenomenon, suggested that this cascade process is fractal, and in a sense he suggested that instead of viscosity halting this process, it might actually diverge down to infinity. We'll address that problem later. So, 2 slides. Kolmogorov's K41 theory that you'll have done in graduate school. It's really based on the Euler equations, which have this scale invariance. And this H is actually free. For Navier-Stokes, it's -1, but for the Euler equations, it's free to vary. And so the trick, which is all explained in Uriel's book, is to take the structure function where you have a point of velocity at a point x, you draw a sphere around it of radius r, you take the velocity on the boundary, u at x plus r, take the difference to the power p, take whatever statistical average you wish, and essentially this means scales like this, according to this scaling invariance, has to scale like that. Okay, now K41 basically axioms say that if the dissipation rate is to be homogeneous in space and time, then H must be a third. So you're talking like SP is R to the P over 3. And that's consistent with the 4/5 law, which you actually can calculate directly. And that's why there's an equals there, the -4/5 epsilon r. So when P is 3, that is consistent with this. And then you do the usual trick of getting the -5/3 spectrum and the Kolmogorov cutoff inverse length scale Reynolds to 3/4 that everybody knows and loves. Now that's K41 in half a slide. But the reality is, as Uriel's book points out, that when you actually look at data, that's not really quite true. And that if you look at SP scaling like R to the zeta p, instead of zeta p being a straight line P over 3, and you can see P is 1, basically, sorry, P is 3, you have it 1 there. Basically, you get a concave curve below linear. And this is attributed to intermittency. Now, we're going to come back to this soon. So, historically, Parisi and Frisch addressed this problem by using a probabilistic argument, and they relaxed this strict H is a third rule to say, well, let's keep the energy dissipation rate remains constant on some probabilistic average. And that allows you some freedom of departure from H is a third to represent intermittency. So they introduced P of R of H as the probability of observing a given scaling of exponent H at a scale R, and that H belongs to a fractal set of dimension DH. And so P would run like this. So that's the codimension C. And then they do some mathematics and they invert a Legendre transformation, and they find that this zeta P is this inf of this object here. And one finds therefore that D of H is bounded by 2 plus 3H. So of course when H is a third, you're bounded by 3, which is the sort of full box dimension. Okay. And then separately, Padhan and Vulpiana suggested a dissipation scale of Reynolds to the 1 over 1 plus H, which would of course be 3/4 at H is a third, but you allow H to vary, drop from a third down into negative values, and this starts to rise. Now there is a bit of a problem with this, as we'll see later, because their definition of Reynolds was pretty horrible. It's fine for a homogeneous isotropic flow, but as soon as you have flows that are not that, then their definition needs seriously changing, but we'll come back. Okay. So I'm now going to move on, it's that fast, just 2 or 3 slides, to the incompressible Navier-Stokes equations. Okay. In 3D, we're going to be on a periodic box, just take L2 bounded forcing. And of course, div u gives you the Helmholtz equation that you have to invert at every time step, etc. So here are my definitions. This bracket means time average up to time capital T. This double bracket is a norm, it's an LP norm defined like this, and therefore I can define a U0 for my Reynolds number based on the response of the Navier-Stokes equations, because the energy is a bounded object. Okay. Now, some quick CFD history as a digression. I think Phil Marcus mentioned, You know, the Orsag and Patterson 72 was the introduction of spectral methods. And I think that was a 32 cube calculation on a CDC 6600, I think it was. Is that right? Yes. Okay. And then as you go down all the big calculations over the years, at 250, I think Bob Kerr's was 256, you get into 512 cubed. Till you get up, Currian and Taylor was 2048 cubed. These were 4096 cubed, and we're going to see a picture that Diego Donzas has led me of this. And there's a for postdocs and students here, there's a very, very nice review article by P.K. Young and Ravi Kumar in PRF, basically talking about all the issues, computing issues, to looking at high Reynolds number turbulence. And it's based on these 18,000 cubed calculations, which essentially, this is basically, it's like state of the art, I think, at the moment. Now, that calculation from 2012 that Diego gave me, essentially, is a Reynolds lambda 1,000, based on 100,000 processes. I suppose these days, it's a fairly typical sort of picture. And as we know, vorticity tends to accumulate on tubes, the red, or filaments, and dissipation tends to accumulate around the outside on green, around there. And that's a very sort of typical type of box behavior where vorticity and strain accumulates. It doesn't just spread itself randomly, it accumulates on thin sets. And essentially, if you look at it spectrally, you see these are highly intermittent flows. Okay, so let's just, before I do some proper Navier-Stokes analysis, just let's look at it more heuristically. Let's take the curl. Okay, here's the curl of Navier-Stokes. Of course, now you've got omega, your pressure's gone, but you've got omega dot grad U, the vortex stretching term, which is also S omega, because omega doesn't see the antisymmetric part of grad U. Now, of course, in 2D, this is 0. Omega points upwards, grad is in the plane, so it's 0. And so, in effect, what you have in 2D is an advective heat equation. And you can basically get omega bounded in L, not just L2, but any LP, and your regularity-wise, for the mathematician, you're home. Okay, but in 3D, of course, this is not 0. And if you just think of it roughly like this, that S has 3 eigenvectors. At any point, it has 3 eigenvectors. They're all spinning round, and omega is spinning round. So momentarily, what omega aligns with a positive eigenvalue, you're going to have exponential growth. And then it spins around more, and if it aligns with a negative eigenvalue, you'll have exponential collapse. So you'll start with very nice, smooth initial data, and then very quickly, you'll get the growth, collapse. And so the data becomes very rough, very fast. Okay. Okay, so basically what we know and recognize, and have done so for a long time, is that you have intermittency is violent spiky departures from space-time averages with sort of quiescent periods in between. So the data gets rough, but then the question is how rough? Does it become singular? You know, what can we say qualitatively? Those are questions that mathematical analysts ask themselves as to how rough and what can we say about it. So this is a bit of a tutorial on Navier-Stokes and what we know. Okay, so let's start with the energy and the entropy. That could be also omega squared because div U is naught. And if you do like 5 or 6 lectures or a chapter of a course, it looks obvious that you could just write this down. But Leray showed in 1934 the existence of what we call weak solutions, which are sort of distributional. And you have to do some fairly hard, rigorous work to actually get to this step. Okay, but it gives you a time average dissipation rate, you time average here. By the way, I'm not going to go into the details, but Charlie Doring and Ciprian Froyas showed in JFM 2002 that you can change this term from an F forcing into a Reynolds number, and this basically becomes Reynolds cubed. So this gives you that result, which just doing a one-line calculation to get the inverse Kolmogorov length, it gives you a bound of Reynolds to the 3/4, which it should do if it's going to touch on K41. So it is an inequality, but it sort of touches all the right numbers. Okay. Now, what other results do we have? Well, Olga Ledezhenskaya in '64 proved regularity, and this is 3D Navier-Stokes, not 2D, 3D, for short times or for small initial data. Hello.
The inequality, the Reynolds 3/4 inequality, is there some limit where you can say that if everything was uniform, then you would actually get it to the inequality? Is there some understanding of when it's saturated?
It would be saturated for really strong initial data, but there are many classes of initial data where that wouldn't be achieved.
I see.
Yes.
Thanks.
Yeah. And then in 1978, Luc Tatar, a well-known French analyst, proved that the time average, and that U infinity means the maximum norm, point-wise, of the velocity field, and I've left out the L's and the N's, is bounded by Reynolds cubed, and that was a big surprise. And then Ciprian Froyas, the great analysts, Colette Guillaupe and Tamam proved now there's an infinite hierarchy of these H's with an exponent that is decreasing, 1/2n minus 1, and those averages are all bounded as well. So when n is 1, you're picking up this, but then there's this hierarchy up to infinity here as well. And then there are actually other results like that. Now, all these results are just weak solution results, and weak solutions are not unique. That's the problem with regularity. They exist, but they're not unique, and you need existence and uniqueness for full regularity and win $1 million for the prize. So this is what we know. Now, this is my own minor contribution. I'm going to synthesize all those results together in one line. Okay, so let's take the Navier-Stokes invariance property, and if we look at these objects here, these norms, this is a power exponent 2m, you find that these norms with this L are invariant, and that this alpha here, which is going to crop up, and you'll see it in Toner 2, is 2m over 2m in n plus 1 minus the box dimension, which is really 3. Okay. And therefore, from this, you can construct a dimensionless family here, like that. And the alpha is a 1 over alpha here. And then all those results of the previous slide, which appeared geographically and temporally in different places, you can roll them all together. And I promise you, this is one theorem only. Okay. You can roll them all together into this theorem that says, D-dimensional Navier-Stokes weak solutions obey this, and this F to the alpha, and field theorists would love this because it's a 4 minus D. Field theorists always like 4 minus D, although I don't personally see the connection here. These are all bounded by Reynolds cubed. And if you put the various N's and M's in of the previous slide, all that list I gave you of bounded objects in the previous slide are all special cases of this. So this basically rolls together sort of all the weak solution results we know. Now I'm doing this because I'm going to show you that Toner 2 has exactly the same result. Okay, so let's move on. Just one more slide of my tutorial and then we can get down to business. Okay, now let's do some interpretation. So here is my L2M norm of n gradients. Now, if you put m is 1, an L2 average, I'm thinking of it this way. Excuse me a moment. If this room was that visualization box that I showed you of tubes and things, okay, from Donzis. An L2 average is just a sort of average visual wash. It's like taking your eyes and just defocusing and just looking at the sort of average. Now you raise M. Raise this M, and as you increase M, essentially what you're doing is you're focusing your eyes or focusing a telescope with a zoom lens on the maximum point. You say, ah, yes, up there, there's the maximum point of vorticity up there. And you're focusing in, like on, so it's like taking a zoom lens and you focus in onto the maximum. And that's basically what this M is. That's what the function of M. We move it between 1 and infinity. And now here's the trick to get a correspondence with the multifractal model. This alpha that I showed you earlier, I can just divide by M and write it as 2 over 2 into n plus 1 minus d, the box dimension, and it's now d over m, so I call that curly d. And so, essentially, whereas that is talking about n derivatives in L2M over the full dimensions, it's exactly the same alpha as if you're now in just L2 of a set whose dimensions are now you've got a whole range of dimensions, 3 over m. Okay, and I'm good, so that's exactly like a multifractal set where you've got a whole range of dimensions. Okay, so I'm going to call that set Fm, okay, and it suggests Fm is multifractal in character. So now this is what we do with it. Okay, to get some correspondence with multifractal model, because the multifractal model is very different. It's homogeneous isotropic turbulence. Navier-Stokes is an evolutionary PDE. They don't look as if there's any comparison, but I think you could say that if you take time long enough and the flow and the turbulence has matured, at least you can make some rough comparison. So I'm going to say, right, well, this dH of the multifractal model, which is bounded by that, I'm going to say is equal to the 3 over m, the curly d, which gives me an inequality relation between m and h. And h min is now this m minus 1 over 2/3. So when you look at m is 1, of course it gives you exactly a third, which is k41. And when you take m to infinity, it says that actually h is bounded below by minus 2/3, which was a result in an independent manner, which I won't go into, that Berger, de Brule and I found in 2022, but I won't go into that. Now, what it's saying now is that if we redo the energy dissipation rate, not over the full box, but over this multifractal set Fm, and that's in there for dimension purposes, you can, because that's embedded in the full thing, you can actually bound it in this manner. And then from epsilon m, you can work out a set of inverse lengths in all the standard fashion, and it gives me 3 over 1 plus dm. Now that formula, with some just general d, was written down by Krejcinen and Oral and Frisch and Vergasola in 91. But that's very long ago, and they wrote down the formula. They had no identification of Fm, and those were the days, if you remember, monofractals, when people said, oh yes, the Lorentz attractor is dimension 2.91, so let's bung 2.91 into the formula. Those were the days when people did that sort of thing. Okay, but what this is saying is that actually dm is really 3 over m, and it gives you a range. Of course, when dm is 3, that gives you k41, and then as dm drops on its continuum down towards 0, the 3/4 actually goes towards the limit of Reynolds cubed. So Richardson was right, there is a dissipation cutoff in that sense, but the problem is, for a physicist, that an inverse length scale like Reynolds cube, you've already hit kinetic theory way before that, but this is mathematics. Okay. Now, just one final thing. Where does that fit with the Padhan-Pandit scale? Well, it's trivial to say that the minimum of the upper bound is actually Reynolds over 1 plus h. So we've recovered the Paladin-Vulpiani scale properly as the minimizer of the right-hand side. Okay, now I'm going to say no more about multifractality and Navier-Stokes. I'm now going to move on. Okay, and if you keep in mind Sriram's talk, he gave us the physics behind how the Toner 2 equations, and that I'm going to take the incompressible deterministic version. Now, of course, that's not the most ideal for real physics, but I want to sort of look at the basic equations that we have. Okay, and these are some of the famous references here and here. And nu is, of course, a viscosity, because this is Navier-Stokes on the left, and this is some form of forcing which platforms at alpha over beta, square root of alpha over beta. Nu is a viscosity. Beta has the dimension of an inverse viscosity, which is important because we're going to define two Reynolds numbers. Alpha is a frequency, lambda is dimensionless, and we're going to be on a box like so. And so now, and this is in this joint paper here, we're going to go into dimensionless variables in time-honored fashion, and we'll now rewrite Toner 2, drop the primes, and now we have two Reynolds numbers. We have the standard Reynolds number, U0 L over nu, which I call Reynolds nu, but we have another one here as beta U0 L. You see, beta is a 1 over nu, so this is the correct way. Okay. So we're going to be dealing with this red version. Now, this is the key slide. If you ignore the alpha U driving term, which is basically pumping energy in to the problem, that's the sort of bacteria wagging their tails, I suppose. The Toner 2 equations have identical scaling properties to the Navier-Stokes. And I don't think I need, if you've understood anything of my first half of my talk, I don't think I need to go through and convince you that essentially everything I've talked about in that first two carries over to the Toner 2 equations. And I've got my alpha 2m over 2mn plus 1 minus d, okay? And what it would do, you do all the work, and I'm not going to do it, and essentially that theorem I wrote down 3 slides ago, where I've got a time average of f to the 4 minus d alpha, essentially is true for Toner 2 equations. So you've got all that range of they're not conserved quantities, but bounded quantities, and they're weak solutions, they're not strong solutions. Okay. So when d is 2, because of that 4 minus d, I've got a factor 2 here. And so in 2 dimensions, I'm going to call these objects Pn. And in 3 dimensions, because 4 minus 3 is 1, I'm going to call them Qn. Okay. 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 So now the question is, now, mathematical analysts love to think of, for a PDE, of is there a global dissipative PDE? Is there a global attractor? And what that means is not just sort of one chaotic solution somewhere in the basin. It's essentially this, that in L2 of whatever your variable is, you want to know, is there a ball into which has certain properties into which from all initial conditions, solutions are drawn. If your initial conditions are outside it, you're sucked into the ball. If you're inside it, you can't escape. Okay, and so basically, as T gets large, all solutions sort of act within this attractor. And what we're interested in is then the properties of the attractor and what's called its Lyapunov dimension. And that takes account of all dynamics. Okay, so that we want to know, is there a global attractor in 2D? Because we know that Navier-Stokes has a 2D global attractor. And so I'm not going to look at the detail, you can work it out. It's very, very simple. You've got this extra integral of u to the fourth, which is very nice to have. Okay, and now what Navier-Stokes doesn't have, and because of that, you know, we can do an inequality and end up with a minus h naught squared. Now Navier-Stokes doesn't have this, so you've got a sort of h naught, but there is a ball for h naught, and essentially if h naught is bigger than alpha naught over Reynolds beta, the right hand side will be negative and h naught will collapse back in. Okay, and there's this nice extra property here that this is being true. Now, you would think, or I thought when I was doing it, well, we'll lift over all the properties of 2D Navier-Stokes, there's no vortex stretching, everything should be okay, and I had forgotten, of course, that you've now got this curl of u mod u squared. And I thought, oh dear, that's a problem. And so you rather glumly work your way through the analysis thinking it's not going to work, and then suddenly this extra piece of information here rescues you. Very nicely. But what you actually can't prove is a sort of a ball of finite radius, which you can prove for 2D Navier-Stokes. The bound that you get for H1 is an exponential bound in time. Now that tells you that any finite time, your H1 or your entropy is bounded pointwise in time, so it cannot blow up. But it doesn't have a fixed maximum because the bound is growing exponentially. So you don't actually yet, I'm not saying it doesn't have a global attractor, but its existence is still open, but solutions are regular. Right, so move on. So more general estimates, and you don't want to see how I got these. It's like, took me a month to do this. It's a question of how you choose your u naught. The conventional choice is root alpha over beta, but another choice is to take that where Reynolds nu is 1. Because I've now got two Reynolds numbers, I'm going to have much richer dynamics. And I've just done some estimates for you for Reynolds nu much bigger than Reynolds beta, and all these objects are bounded. How I did it doesn't matter. But you've got a whole hierarchy of things, and you have to work very hard to get these things, but they all exist. Okay. And Kiran and Padhan and Rahul then did a selection of plots. Now this half is u naught is root alpha over beta. That's panel A. And that half there is u naught nu over L. And you can see that as you would expect, there's fundamentally different dynamics as you would expect to get. If Reynolds nu is just 1, as opposed to very big, you would expect very different dynamics. But it's a much richer set of dynamics, as you would expect, than 2D Navier-Stokes. So it looks as if it's different than Navier-Stokes turbulence, and it is different, but mathematically, it's not so different from the way you look at it. Okay, move on. 3D estimates. Again, these Qs, this is exactly like the Fourier-Guillaume-Temam hierarchy. You get no more than you can get for 3D Navier-Stokes. The open Clay prize problem for 3D Navier-Stokes is exactly the same for this. But we can at least get some information. And they the boys put in a lot of work, a lot of computing time at Indian Institute of Science to do 3D plots, because that's not so easy. Now, this isn't really telling you much unless you look at the real detail. So let's move on. Now, here's part 4. I'm getting through things very quickly, actually, but never mind. We have a longer break. I'm now going to move on to Toner 2 Swift-Hohenberg, which, as I said, is now you've got anti-diffusion, and then you've got the bi-Laplacian. And I'm going to do the same rescaling into a dimensionless version, and I've got the Reynolds beta second Reynolds number, and now I've got what's called Reynolds gamma naught for here, that's like the Reynolds nu, but also this delta. Now this delta is actually important. I looked up Shamridi's Nature Physics paper and took the numbers, and this basically, this is, when you look at it, it's something like 1/80, so you've got a factor of 80 in there, which is quite significant when you're multiplying it on that. Okay. So we've got these 2 Reynolds numbers, or almost 3 Reynolds numbers really. And what we have, okay, now I don't want to go into detail. Toner 2, because it's got this Laplacian term, mathematically everything's nice. There's no problem, you can calculate what you like, everything's regular, whatever averages you want, you can get, you don't need to see it. We have good explicit estimates for everything, and there does exist a global attractor into which solutions are attracted. And that's for this is ongoing work. And so, essentially, now, including myself, the older members of the audience who remember the Kaplan-York formula from our younger days, the Kaplan-York formula, which is what we're going to estimate, is a way of taking a dynamical system, say, of a set of ODEs, for instance. And what they did was this. Lyapunov exponents control the growth of attraction of volume elements in a finite dimensional phase space. So maybe this is say a set of ODEs, for instance. And this N0 is essentially the following. You sum your exponents. And if N0 minus 1 of them is positive, and then you add 1 more in, and that changes the sign of the sum, then that value of N0 basically bounds above the Lyapunov dimension of the attractor. And N minus 1 bounds it below. This is and this is what's called this. You can prove from that, you can get this. And this is what's called the Kaplan-York formula, which was quite famous in its day. Now that's basically for ODEs, finite dimensional. And in 1985, Peter Constant, Chipper and Foyce, they reworked the whole idea for a global attractor for a PDE, and you're in an infinite dimensional phase space now. So instead of having a finite dimensional attractor, you've now got L2, and you're in this ball, this fuzzy ball, your global attractor into which all solutions are drawn. You're basically breaking it down into volume elements, and some of them are exponentially increasing and some of them are not. And that's where your mu's come from. Okay. And so what you do is you form a volume, you linearize like this, you take your deltas, you form a volume in that way. These wedges are like, vector products. You form a volume, you take your linearized operator from your equation, and from that, you can actually show that this V satisfies this equation. And this trace is essentially a projection. It's a projection of taking the M onto, now your attractor, you're in L2, you can then say that your global attractor is spanned by a set of orthonormal functions. And you project onto those orthonormal functions here. And that's really just what that trace there means is this. You take n is what sum 1 to n, and these are your orthonormal functions. And that is the sum of your Lyapunov exponents there. So that's their way, Constant and Foyce's way, of getting from here for finite dimensional to infinite dimensional. Now, these phi's, because they are orthonormal they have these simple properties. And of course, for the negative Laplacian, of course, you do one integration by parts and you get to this. And we will need the bi-Laplacian as well, because this is Toner 2 Swift-Hohenberg. Now, what gives us a really good result is that in 1983 or 5, two well-known guys, Elliot Lieb and Walter Thirring, two names from the theoretical physics in the past, to everybody's astonishment, proved that there's a new set of inequalities. That for orthonormal functions phi, if you take the sum, put it to the dimension plus 2 over d, integrate, then that is bounded by this, and the c is not a function of n. Now you see you're reducing the nonlinearity. Say d is 3, that's 5/3, d is 2, it's squared, d is 1, it's cubed. Okay, it was remarkable, everybody was, and they got these from basically considering Schrödinger equation inequalities. Somebody noticed it and lifted the idea over, and you can use these. There's about 15 pages of calculation from here to the result, and I'm just giving you the result. And essentially, our n0, which bounds our Lyapunov dimension for 2D, goes like this delta to the -1 Reynolds gamma to the 3/5. That's just a correction set. And then the Reynolds beta to the -1 is 1/5. And physically, I think what is important is how insensitive this estimate is to Reynolds beta, because it's a 1/5 power. Okay, and 3/5 is pretty good. I mean, how do you interpret Lyapunov dimension? Well, if you read Landau and Lifshitz, they essentially say, roughly, it's the number of degrees of freedom of the system. And so you interpret the Lyapunov dimensions, the number of degrees of freedom of the system, and therefore that tells you what your resolution length is. So if this is 2D, your resolution length would basically be inverse resolution length will be this Reynolds to the 3/10, because which is computationally achievable. And in 3D, and that was a much more painful calculation, essentially it's 21 over 16, but then you need 1/3 of that, so it's 21 over 48. So that's sort of like Reynolds to the 1/2-ish. So that's, again, not too bad. So computationally, it's telling you that these are pretty good results. And this work is really very, very, very new, just sort of the last few weeks, which we're trying to sort of do numerical stuff to confirm it or see how close it gets. And essentially, it's only 10:15, but I've finished. So thank you.
All right, we've got plenty of time for questions.
The invariance properties of Navier-Stokes and toner 2 or beyond toner 2 are very different. In the one case, you have Galilean invariance, in the other, you have an absolute frame of reference, a meaning for the absolute velocity. And yet, there's this much in common amongst them. I mean, you say something about why? Or was that what the talk was supposed to have told us?
No. It's a good point. The talk is a consequence of that. The why, I don't know. It's basically trying to point out that, from my tribe's point of view, it has all these really nice properties, the same as and more, and richer than Navier-Stokes.
So just one follow-up thought on this, which is that if you take toner 2 or toner 2's Sternberg, if you like, and work at the threshold of where you get a spontaneous velocity, so your alpha naught equal to 0. You don't really have Galilean invariance there, but you have a much smaller cost for changing velocities and a much, right? Is there anything special about the behavior at that point?
Well, I think very small alpha, strange things would happen. Because, of course, I haven't gone into the detail or written down all the different limits.
Right.
One would have to rework all the estimates for all the different limits where the parameters go into different regions.
Right.
Because there wasn't time, and I don't think people would be interested in a talk like this.
Okay.
Yes.
Another question?
So this is a kind of follow-up, really. and it's a slightly more technical version of the same question, but somehow you had an equation with lambda, which is the coefficient of the Reynolds-like term, and you somehow rescaled it so that lambda became 1 in the term 2.
And it goes into the Reynolds number.
Yeah, but so what? Then you could do that with Navier-Stokes, you're saying?
We don't.
I don't believe you
We
can.
don't have a lambda in Navier-Stokes.
No, what I'm saying is I can have a family of equations.
Okay.
Well, I just start with Navier-Stokes and I insert lambda.
Yeah. Okay.
I've broken Galilean invariance, so I don't believe that's the Navier-Stokes equation anymore.
Yeah.
And yet if I can rescale that into the Reynolds number, it is. So something is
Yeah, but the rescaling into the Reynolds number is the second Reynolds number, Reynolds beta, which isn't there in ordinary Navier-Stokes.
So I can't get rid of it in
No.
Navier-Stokes?
No.
Because there's nothing to put it into.
Exactly.
So okay. So it ends up rescaling a term that is absent in Navier-Stokes.
Precisely.
So you can rescale the length and lump all the sins into redefining the pressure or something, right? It's only Navier-Stokes without a density. There's only one.
Well, I'm still claiming that Navier-Stokes without Galilean invariance is not Navier-Stokes. It must be something else.
No, but if you have only one, sorry, I don't want to we can fight afterwards.
Yes, let's fight afterwards.
I think there was another hand up over here.
I was very intrigued by your global regularity results. So as soon as you have the hyperdiffusion, you get the global regularity.
You get global regularity, yes.
So, but this may be a very technical question, but if you would consider, hypothetically, a fractional Laplacian, do you know to which power you would need to get the global regularity?
Well, I think it would, for ordinary Navier-Stokes, the fractional power is the Lyon's result from 1959, which is 5/4. For the rest of the audience, if you raise the power of the Laplacian, the result Jacques-Louis Lyons did in 59, then essentially you raise it and you raise it, and when you hit 5/4, then Navier-Stokes, you can prove Navier-Stokes 3D are regular. And I think it would be the same result because the anti-diffusion you can sort of deal with. So I think it will be the same result.
I don't know if I missed it. So given a turbulent system, whether it's a simulation or experiment, how do I evaluate your Reynolds number beta of the system?
How do I evaluate?
Evaluate the Reynolds number beta of a turbulent system. If I have some data, for example, or we know some physical property of an experiment or a simulation, like how can I get what should be the?
Well, what is it? It's beta L.
It's like,
U naught.
I think it's more like what's the physical meaning of the beta
So,
of the system?
so you would need, I mean, Shamridi, you can answer. You basically need the data from the experiments for Reynolds beta. It isn't something universal. It's something you have to calculate for each.
Another one here? Yeah.
These ideas, John, go through if you've got a more complicated 2D system. You know, if you've got 2D MHD, for example, so you've got the 2D, you've got an active scalar equation as well.
Yeah.
And you carry all.
I have not really looked at 2D, but from memory, from what people say, there is an analysis problem with 2D MHD that isn't there in 2D Navier-Stokes, and I can't remember why. I would have to look that up, but I think that that the magnetic field causes problems.
Yeah, it often does.
Is that true?
It's an understatement of the week.
Is that true if you add in like a Boussinesq kind of approximation too, or you have the active scalar?
And I don't think an active scalar is a problem. Compressibility is a serious problem, which is why we've gone to the incompressible limit. And adding noise, of course, changes dramatically a lot of the properties. So this is just a stripped down version of
there's another simplifying limit of toner 2, which is where you drop the pressure term altogether, right? Which is as though you start out with a compressible toner 2 with a concentration field.
And you drop div u is naught as well.
Yeah, forget div u is naught. Imagine you had a system made of particles, and now you allow the particles to be born and die, so the number density is no longer a slow variable. So you have the nonlinearity of toner 2, which is the Navier-Stokes nonlinearity, and the u squared, I mean u cubed and all that. But no gravity.
You can deal with that.
The other John Toner calls it Malthusian, annoyingly enough, because you have birth and death.
In a very non-Malthusian way.
Yes, yes. It's a simpler problem because unconstrained by div u equals 0.
Mathematically, because you have a maximum principle that you can use, which without when the pressure's not there, it's the pressure that stops you getting that. So again, it's a different mathematically, it's a different universe.
Right, but you haven't looked.
I haven't looked at it. I'm like I say, I've just personally been working on this for a couple of years, doing a lot of reading.
Any last questions? All right, let's thank John again.